If you look into AI video generation, you might have heard of optimization techniques like sage attention, flash attention, EasyCache, distillation, etc. But what are they? Let's find out.
We're going to uncover exactly how massive AI video and image models are able to run, literally generating completely new realities pixel by pixel without absolutely melting our computers. If you've ever wondered how your hardware actually survives this modern miracle, you are in the right place for this explainer. So, to understand the solution, we first really have to respect the sheer scale of the problem. Generating a single image is tough enough, but why is AI video so uniquely expensive to run? It's just a massive computational burden. The model doesn't just make one image. It has to process dozens, sometimes hundreds of frames. And more importantly, it has to keep objects, motion, people, and lighting perfectly consistent across every single one of those frames over time. We're talking about a staggering amount of math here. Okay, here's the game plan for this explainer. We'll start with the core inference problem, move into how we reduce and reuse work, look at making the math cheaper, see how all these optimizations stack together, and finally, look at how this applies to text-based LLMs. Let's kick things off with part 1, the inference problem. We've got to frame this computational challenge before we can solve it. Think of this 4-part framework as our mental map for today. 1. Run the model fewer times. 2. Stop repeating work that barely changed. 3. Make the remaining calculations cheaper. And 4. Use the GPU more efficiently. Let me tell you a secret. Every scary, complicated piece of jargon we're going to encounter today is literally just trying to answer one of these 4 specific questions. Moving right along to part 2, reducing and reusing work. This is all about attacking generation steps and repetition. Basically, figuring out how to just do way less overall work right from the jump. The most obvious way to do less work? Just take fewer steps. Normally, a diffusion model gradually turns noise into a pristine image over, say, 30 or 40 separate steps. That means running a giant neural network 40 times. Step distillation trains the model to accomplish that exact same job in just 4 to 12 steps. So instead of dozens of tiny tweaks, the model actually learns to make a few large, highly intelligent improvements. It's an absolutely massive computational win right out of the gate. Now, think about editing a huge Photoshop document. Moving one single object shouldn't require rebuilding every unchanged layer from scratch, right? That logic is actually the foundation of things called diffusion caching and EasyCache. Even with fewer steps, neighboring steps in an AI generation often look incredibly similar internally. If the AI calculates a really complex background at step 10 and literally nothing changes by step 11, why on earth would we do the math again? Diffusion caching simply saves and reuses those intermediate results. So the crucial point here is how this concept applies to something called shared attention. Attention is just how AI models figure out which parts of an image or video relate to each other. Between neighboring steps, those core relationships barely shift. So shared attention says, hey, let's just reuse that previous relationship map. But quick heads up, we do have to be careful here. Reusing these relationships for too long without refreshing them can actually start to hurt the fine visual detail and motion consistency. To really get this, let's compare dense and sparse attention. Dense attention is like a 10,000-person meeting where every single attendee is forced to chat with every other attendee. It's absolute chaos, and it takes forever. Sparse attention steps in and reduces compute by pointing out the obvious. A patch of pixels representing a hand definitely needs to look at the arm next to it for sure, but it does not need a strong, mathematically intense connection to an unrelated patch of sky in the background. We just deliberately skip the math for interactions that don't matter. All right, on to part 3, cheaper math and better hardware. We've eliminated all the work we possibly can. Now, how do we handle the math that we absolutely cannot skip? Enter flash attention. Remember, sparse attention was do fewer calculations. Flash attention is do the exact same calculations, but with way less data movement. Think of cooking in a kitchen. If you constantly take an ingredient out of the cupboard, use it for 1 second, put it back, and then immediately have to fetch it again, you're wasting all your time walking, not cooking. Flash attention organizes the math so the useful data stays right on the counter, right next to the GPU's active workspace, avoiding a massive waste of time. Next, we have sage attention, which asks a really practical question. Do we actually need such incredibly precise numbers? AI models usually calculate with 16-bit precision. But think about measuring the distance between 2 major cities. You just need the miles, right? You don't need the answer accurate to 15 decimal places. Sage Attention uses lower precision arithmetic for certain tasks. Using smaller numbers saves a ton of memory bandwidth and speeds everything up, with almost zero noticeable drop in visual quality. Now, taking that smaller numbers idea to the absolute extreme gives us quantization. This literally shrinks a model's weights entirely, from say 16-bit down to 8-bit or even 4-bit formats. I really want to emphasize this. Quantization's biggest superpower isn't actually saving memory space. Its real superpower is massively speeding up how quickly data can be fed to the GPU. Modern GPUs are insanely fast calculators, and honestly, they're usually just sitting around waiting for data to arrive. Smaller data means faster feeding, which means a radically faster model. Finally, for this section, we have fused and custom kernels. This is the last squeeze of efficiency. Imagine the GPU reading data, calculating it, saving it, and then immediately reading it again for the very next step. Fused kernels combine multiple operations into one continuous, highly optimized task. Read once, calculate a bunch of things, save once. It's just pure, brilliant software engineering to reduce GPU overhead without altering the model's actual behavior at all. Which brings us to the climax of our journey. Part 4, the optimization stack. Let's see how all these distinct, brilliant pieces actually fit together in the real world. When you look at this comprehensive summary of trade-offs, pay special attention to the quality risk column on the right. Pushing any of the top work reduction techniques too far, like caching too aggressively, can definitely cost us visual detail or temporal coherence. The hardware efficiency techniques at the bottom, though, those carry very, very low risk. Because when you stack these techniques together, you can see how they build. This stack proves these are absolutely not competing techniques. It's a compounding layer cake. You run fewer steps, you reuse work in the steps you do run, skip unnecessary interactions, calculate what's left incredibly fast with smaller numbers, and wrap it all up in custom GPU commands. Stacked together, this is exactly what creates an aggressively optimized lightning-fast video model. Let's pivot slightly for part 5. What about text-based LLMs? We've talked a lot about video and images, but text models generate sequentially, word by word, introducing completely different bottlenecks. For LLMs, we rely super heavily on KV caching, which essentially remembers past context, so the AI doesn't have to reread the entire conversation for every single word. We shrink that massive footprint with KV cache quantization. But honestly, the coolest trick here is speculative decoding. It brilliantly uses a tiny, super fast model to run ahead and guess the next several words. Then the massive smart model just double-checks the work. Wrap that up with continuous batching to group different users' prompts together, and you ensure the GPU is constantly maxed out. So, if you take just one thing away from this entire explainer today, let it be this simple progression. First, remove work entirely. Then, make the remaining work cheaper. Finally, execute that work as efficiently as possible. Keep this simple takeaway in mind, and you will always understand exactly how all modern AI optimization operates, no matter how wild the jargon gets. And that brings us to the bleeding edge. As generative AI leaps from making standard flat video into generating highly complex, fully interactive 3D worlds in real time, which of these optimization layers will become the ultimate breaking point? Are we going to hit the absolute limits of hardware bandwidth first, or will we run out of clever math tricks? It's a pretty fascinating question to ponder. Thank you so much for joining me for this explainer, and keep your curiosity focused until next time.